Hello. So welcome back now. We are going to continue with what we have been discussing. Recall all these concepts and make sure that you have understood these concepts before you start looking at this lecture. We are going to continue with looking at heterogeneous azeotropic distillation. That's what we have been discussing in the last lecture. We are going to continue with heterogeneous azeotropic distillation. We looked at pyridine water, we looked at acetic acid water. If you don't recall, please go back to the previous lecture and understand for yourself. Here's the next one more example: hexane and ethyl acetate separation. So hexane, again, hexane is boiling point 68.7, ethyl acetate 77.1. They form an azeotrope at 65.2. So minimum boiling azeotrope with 66 mole percent hexane. Methanol can be added to separate these azeotropes, separate this or break this azeotrope. Methanol forms azeotrope with hexane. Methanol also forms azeotrope with ethyl acetate. Methanol and hexane are only partly miscible with each other. So it's an example of heterogeneous azeotropic distillation. So I want you to draw a residue curve map and propose a process flow diagram. I want you to draw a residue curve map with, let's say, hexane at the topmost vertex, ethyl acetate at the origin, and methanol at the other side, the third side of the triangle. Okay. So what I want you to do, draw is hexane at the top. So I want you to draw an RCM like this: hexane at the top, ethyl acetate at the origin, and methanol here. So this is the third side of the triangle. So hexane and ethyl acetate form an azeotrope. So hexane, ethyl acetate, there is one azeotrope here, right? Methanol forms azeotrope with hexane. There is an azeotrope here. Draw them properly based on composition. I'm just drawing a rough. Methanol and hexane are partially miscible with each other. Methanol forms azeotrope with ethyl acetate. So one more azeotrope is here. Now methanol and hexane, they form two phases. So the two phases are like this. Methanol rich phase is heavier, hexane rich phase is lighter, and the tie lines would be like these. Okay, the actual tie lines will come from composition. I'm not giving you that, just let us approximately indicate. Now I want you to draw the RCM, approximate RCM along with the two-phase region, and propose a process flow diagram to separate hexane and ethyl acetate. Pause, do it for yourself. Pause, do it for yourself. Pause, don't go forward, don't cheat. Do it for yourself. Even if you don't get an answer, that's okay. But attempting is important. Attempting will force you to think. So pause, pause, pause. Okay, here is how the approximate RCM looks like. Hexane is here, ethyl acetate is here, methanol is here. This is one azeotrope between ethyl acetate and methanol. This is another azeotrope. This is a minimum boiling azeotrope, so the residue curves are pointing here. The residue curves are pointing here. Methanol, ethyl acetate. Is it a minimum boiling, maximum boiling? Well, let's go back and see for ourselves. Ethyl acetate, methanol, ethyl acetate and methanol, 62.1. So it is lower than methanol as well as ethyl acetate. So it's also a minimum boiling azeotrope. So the residue curves are here. Hexane methanol, also a minimum boiling azeotrope. So the residue curves are like this. Now if you see, you will have, if you start taking points around this minimum temperature 50.6, if you take points like this is the composition, then you will go towards the azeotrope. If you are left of the azeotrope, it will go towards the methanol. If you are on the right side of the azeotrope, you will go towards this. If you are on the right side of this azeotrope, somewhere here, oops, somewhere here, it will go towards ethyl acetate. If you are on this side, it will go towards this 64.8 and then towards ethyl acetate. And here, if you are on the other side of ethyl acetate, of this azeotrope, it will go towards the azeotrope and then to hexane, right here. So there are three distillation regions and two distillation boundaries. Okay, one region like this, one region like this, another region like this. Now, how are we going to separate? We have to separate hexane and ethyl acetate by adding methanol, right? So suppose we have an equimolar mixture. This is our feed, equimolar mixture. Suppose I add methanol, then we would be somewhere here, a line joining these 2 points. Suppose I am at the midway, I add 1 mole to 1 mole. Then I would, this is my feed to the distillation column. Now if I distill, what will I get? Look at the residue curves. The residue curves are like this. So bottom I will get ethyl acetate, top I will be able to get this. This is my feed. Suppose this is my feed. At the top I will be able to get this azeotrope, which will split into 2 phases. One phase like here, hexane rich phase, another is methanol rich phase. Now we can take it to respective distillation columns, because this is not a pure phase. Methanol phase is not pure. The heavy phase in a liquid-liquid separation is not pure. The light phase in the liquid-liquid separation, hexane phase, is not pure. I still have substantial methanol. I still have substantial methanol hexane here. Okay, so I will have to send it to separate distillation columns and recover. So propose a process flow diagram. Right, so here is how it will look like. So this will be my feed. So this will be an azeotropic column. I will get essentially pure ethyl acetate at the bottom. At the top I may get an azeotrope which will split into 2 phases, hexane rich phase and methanol rich phase. The methanol rich phase I will send it to a column which will recover methanol at the bottom. See, this is the methanol rich phase. If I send it to a distillation column, I will get essentially pure methanol at the bottom, but top will be azeotrope. So that top azeotrope, we can send it back to the decanter after condensation. Of course, we are not showing the condensers in this scheme. Hexane rich phase, you see the hexane rich phase? Again, if I distill this hexane rich phase, I will be able to get hexane at the bottom and methanol at the hexane azeotrope at the top. So I will get this azeotrope. Again we will condense, we will send it to this decanter. It will split into 2 phases, methanol rich phase, hexane rich phase. We will recycle to respective distillation columns. So if you think about this as your plant, you have separated the hexane ethyl acetate mixture into essentially pure ethyl acetate, essentially pure hexane. The methanol just keeps on recycling back and forth in this column, in this stream, because there is methanol here also. Methanol in this column, methanol in this stream is there, so I will get methanol hexane azeotrope which is recycling here. Here I will get methanol hexane azeotrope which is recycling here, and of course the pure methanol we can recycle back to the azeotropic column. Okay, I hope you have understood. If not, go back and revisit this lecture as many times as you want till you are able to understand. Pause, don't go forward. We are going to take some more examples. Okay, another example, butanol and butyl acetate. Again, when you generate butyl acetate ester is important from different perspective, from various esters of butanol are useful in different ways. Butyl acetate is useful in different ways. So it is made from butyl acetate, is made from butanol and acetic acid. So I get a mixture of butanol and butyl acetate which form an azeotrope. Now water can be used to separate this azeotrope. Why? Because now water forms an azeotrope with butanol, water forms an azeotrope with butyl acetate. There is also a ternary azeotrope of butanol, butyl acetate and water. All these compositions and temperatures are given here. I would like you to draw a residue curve map first. Draw a residue curve map, approximate, along with the 2-phase region, because now butanol and butyl acetate are miscible in all proportions, but butanol water and butyl acetate and water are only partly miscible. They form two phases. So I will have aqueous phase and I will have an organic phase. Aqueous phase will contain essentially water, little bit of butanol, butyl acetate depending on the composition, and organic phase will be butanol, butyl acetate depending on the composition with little amount of water. Draw an approximate RCM along with two-phase region. Now here the two-phase region is not that straightforward because I have two-phase regions. So I would like you to draw the residue curve map with butanol at the top, butyl acetate at the bottom. So I would like you to draw the RCM like this: butanol at the top, butanol at the top, butyl acetate here, and water here. Now butyl acetate and water form a two-phase region. So one two-phase region is like this. Butanol and water also form a two-phase region because butanol water is only partly miscible. So the second two-phase region is also going to be like this. So as a result, the combined two-phase region is going to be something like this. In this part, I will have two phases. Here I will have a single liquid phase. Okay. This is how it is going to look like. I mean, we need to know the exact compositions, but that's okay right now. Right now, what we are only worried about is how to do the distillation, how to think about a sequence of distillation columns. So if you have understood so far, then draw an approximate RCM and go forward. So pause the video, don't go forward unless you have understood all this. Okay, so here is how the residue curve map will look like. Okay, so first of all, butanol, butyl acetate and water. These are the three phases. Now butyl acetate water, there is a minimum boiling azeotrope here. So the residue curves are all pointing away from this azeotrope. Butanol, butyl acetate, there is an azeotrope. It's a minimum boiling azeotrope. Look at these temperatures. Don't just believe, don't just nod your head. Look at these temperatures and see whether it's a minimum boiling azeotrope, maximum boiling azeotrope. I'm just going a little fast, but you can always pause and do it for yourself first. Butanol water, there is a azeotrope. Again, it's a minimum boiling azeotrope. So residue curves are pointing away from the azeotrope towards the butanol phase. Okay, now if you see, the ternary azeotrope is here. This is the ternary azeotrope. See? And that's the lowest temperature. That's the lowest temperature. So we are going to take different points around this azeotrope and we are going to see where the compositions are going to go. So if I take point somewhere here, one of the residue curves will be like this. If I take composition here, one of the residue curves will go towards here. Oops, I'm so sorry. Where was that azeotrope? Butanol and, oops, sorry, that azeotrope was here. Sorry. This is that azeotrope between butanol and butyl acetate. Let's just check. Butanol and butyl acetate. Yeah, 18 mole percent butanol. Sorry, my mistake. So that azeotrope is here. Right. So the residue curves are here like this. Not this. This is the feed, I think. Okay, so if you start somewhere here, we are going to go towards this azeotrope, but then we are going to come towards this butyl acetate. If we are on this side, it will go towards here and to water. It will go towards this azeotrope and then to water. Here, if we are on this side, it will go towards this azeotrope and to water. If we are here, we are towards this azeotrope and to water. Oh, sorry, and to butanol. Right? So I am having distillation boundary. One boundary is here. Let me just highlight the boundary. So this is one boundary. This is another boundary, and this is another boundary. So I'm going to get three regions. Now we can get rid of all of these lines. I get one region, I get another region, and I get third region. And this is the two-phase region. This is the two-phase region. Anywhere here in on the right side of this two-phase region, I have two phases, and on the left I have a single phase. So single phase is here, and these are all the tie lines. This is one tie line, this is another 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 tie line. See? Now think about the separation. What do we want to separate? We want to separate butanol and butyl acetate, right? So let's say our feed contains, let's say 50% butanol, 50% butyl acetate. Let's say somewhere here, this is our feed. Now if you add water, right? Maybe we will add some amount of water so that we end up into this two-phase region. I could distill that. I'll get water, but do I get water? Am I interested in getting water, or am I interested in separating butanol and butyl acetate? I'm interested in separating butanol and butyl acetate, isn't it? So I better end up somewhere in the single phase region, somewhere within this distillation boundary. I better work with this distillation boundary. Only if I am inside this distillation boundary will I get butanol or butyl acetate as one of the pure phases. Do you see? If I am in this region, I will be able to get butanol as one of the phases by distillation. And if I am in this region, I will get water as one of the phases by distillation. But getting water is not one of our objectives. Our objective is to separate butanol and butyl acetate. Do you realize? So if I start with this and I add water, maybe I will remain somewhere here, you see. Suppose I remain here. Oops. Suppose I remain here. Now I will get butyl acetate as one of the phases, as the bottom of the distillation column. I will get this as the top of the distillation column. But does it help me? It does not help me. So what I want to do is I want to end up into the two-phase region here. So I want to end up with a distillate inside this two-phase region. So if this is my feed, I will get bottom as pure butyl acetate. If I get this as a feed, now it will split into two phases along the tie line. The tie line would be essentially pure water, aqueous phase, and an organic phase, which is here, right? Now I want to do something so that I cross over into the other region, so that I can get butanol at the at the bottom of one distillation column. So if I end up with this as a feed, I can distill out butanol as a bottom, and the top I would get this. Now I can mix this stream and this stream. I can mix this stream and this stream so that I end up into this as my feed to first distillation column. You see? So feed to the first distillation column, I can get, so you can look at either sequence, you can look at it any way you like. So if this is your feed is at point number A, so this is my feed, point number A. I end up with butanol at the bottom. I end up with a two-phase mixture. I recycle water, right? I recycle water. So suppose what I do is I add so much amount of water now. I add so much amount of water. So there can be multiple possibilities, multiple solutions. One solution is shown here, right? So you don't worry about Don't say that this is the only solution. So I take water, so I take this 50-50 mixture, I add water, so that I end up at this point B, or somewhere here, somewhere at this point B here. This is my point B, right? And I do distillation, so I will get butanol at the bottom, and I end up with this point very close to this distillation boundary as the top of the distillation column, and bottom of the distillation column would be butanol. See, now this point B will split into two phases, the aqueous phase and the organic phase. Aqueous phase will essentially be pure water. That's how the tie line is. That's how the tie line is. The tie line is at pure water, and this as the tie line somewhere here, L2 if you like. L2 is a tie line, L2. Now this L2, I am on the other side of this distillation boundary. This is the distillation boundary, remember? Now because of phase splitting, I have gone to the other side of this distillation boundary. First I was on the right side of the distillation boundary, I could get butanol. Now I am on the left side of the distillation boundary, now I will get butyl acetate from this column. And top I would be able to stream D, which I will recycle to the first column. See, so the feed to the first column, I want to ensure by recycling, I want to ensure that feed to the first column, I am on this side of the distillation boundary, so that I can get pure butanol, and we end up at the pure butanol at the bottom, and we end up at the top of the column on this boundary. Second distillation column, now after phase split, I ensure that I am on this side of the boundary. This is my L2, the feed to the second distillation column. Now I will get pure butyl acetate at the bottom, and somewhere here, which is close to this boundary, as a distillate. Now this distillate and this essentially pure water I recycle, so that I end up somewhere here on the feed to the first distillation column, on the other side of the boundary. So you see how these boundaries are helping us to decide which component is going to get distilled and which component is going to come to the top and which component is going to go to the bottom, right? Very tricky separation, but it can be done. Okay, so see for yourself, okay. The last example that we are taking is azeotropic distillation of ethanol and water using benzene. Again, benzene is a light entrainer because benzene water form an azeotrope, which is the lightest of them, lowest temperature, so that goes to the top of the column. Now benzene forms a minimum boiling azeotrope with water, with ethanol, and ethanol benzene water form a ternary azeotrope. This is a very complicated situation. I want you to draw an approximate residue curve map. Benzene water are immiscible with each other, and let's say the feed contains very dilute ethanol. Okay, so this kind of situation is when you want to make biodiesel, say for example, or when you want to make ethanol to be blended with fuel. I want to make ethanol by, let's say, fermentation. I made it using fermentation, but fermentation will give us maybe 5% ethanol, 6% ethanol, maybe maximum 10% ethanol. So I have a dilute ethanol, I have a lot of water. I want to make it pure ethanol so that it can be blended with petrol. Imagine what will happen if water goes in your engine. Your engine will just not burn, it will just stop working. So I don't want water going to engine. Ethanol, I want it based on a renewable resource. I can do fermentation, biomass, I can do fermentation. You might have heard of the words like 2G ethanol, 3G ethanol, and so on, coming from fermentation essentially. This ethanol, if I want to blend it into petrol, sustainable resource, I want to make ethanol in a sustainable way, fuel in a sustainable way. Ethanol is a sustainable fuel because it can be made by fermentation of biomass, and therefore the feed will contain dilute ethanol. And getting pure ethanol from such a dilute mixture is a challenge, and benzene is used as as a as a light entrainer to do heterogeneous azeotropic distillation of ethanol water. Now this case study is discussed in detail in the book, Cedar's book, Separation Process Principle. That's what we are using as a textbook. So we are not going to go in great amount of detail in this case study. You can always read very carefully what the book says. I'm just going to show you an approximate residue curve map, and I want you to propose a column strategy. Okay, so residue curve map will look something like this. So if you talk about ethanol, water, and benzene, now draw this for yourself, right? This is the two-phase region. This dotted line is the two-phase region. Anywhere here we are having two phases. It will split into a water-rich phase. These are the tie lines. Water-rich phase, this is a tie line, and a benzene-rich phase. You see, this part, it is very close to the axis. So essentially we get pure water here. Essentially we get pure benzene here. Right? Toluene, same way. Xylene water, same way it behaves. Water, wherever water is there, azeotrope with toluene, benzene, xylene, they all show this two-phase region like this, with essentially pure organic phase, essentially pure water phase at under the dilute conditions. But of course, if I have too much ethanol, then it forms a homogeneous single phase in this part. Okay. So draw the residue curve map. Make sure that your residue curve map is like this. There's one azeotrope here between benzene and water. It's a minimum boiling azeotrope. So residue curves are all pointing away. Ethanol water, again minimum boiling azeotrope here. Residue curves are pointing away from the azeotrope towards water and towards ethanol. Ethanol benzene, again minimum boiling azeotrope. So residue curves are all pointing towards benzene and towards ethanol, away from the azeotrope. This is a ternary azeotrope. Ternary azeotrope, what is the temperature? Let's recall. Ternary azeotrope 64.1. That's the lowest temperature. 69, 67, 80, 78.4, 78.2, 100. Right? That's the lowest temperature. So this is the lowest temperature. Now, so if you take points around this azeotrope, you will see that if your points are somewhere here, you will go towards water. If you are here, you will go towards benzene. If you are here, you will go towards the azeotrope, then to water. If you are here, you will go towards the azeotrope and then to ethanol. If you are here, towards the azeotrope and then to ethanol. If you are here, towards the azeotrope and to benzene. So you are going to get now 3 distillation boundaries. So let me just highlight these distillation boundaries. So one distillation boundary is here. Another boundary is here. Third boundary is here. So now, if my feed mixture is a dilute mixture, one is, of course, I can use a pre-concentration column and reach the azeotropic conditions very quickly. So one of the options of feed is a dilute ethanol. That means, let's say 10% ethanol. So feed would be here. One is I could use a pre-concentration column and get water out of the bottom of the distillation column and maybe make my feed somewhere like this, maybe 80% ethanol. Okay. But see the idea, if you are in this region and I do distillation, I will get water at the bottom of the distillation column. But top, I would end up maybe either on this boundary or this boundary. If I have to get pure ethanol, I need to end up into this region of my distillation boundary, in this distillation region bounded by these two distillation boundaries. I want to end up somewhere in this region, and then if I do the distillation, I will get ethanol at the bottom of the distillation column. Do you realize? That's the whole trick, how to go from left side, from this distillation region. We were on this side of the distillation region, how to go from left side of the region to the right side of the region. That's the whole trick of doing this distillation. And that's how the distillation boundaries, that's how the residue curve maps help us. Okay. Think about it for yourself. Read Cedar's book if you want. There are several solutions that are proposed. I'm just going to show very quickly what the solutions are, right? The details are there in Cedar's book. Read and understand for yourself. One solution is here. This is your pre-concentration column. Essentially, you get water out of the bottom. You are having essentially the ethanol water azeotropic, very close to the azeotropic mixture here. So this is your azeotropic column. Now, if I end up into this region, if I end up somewhere here, I can get ethanol at the bottom and I can end up into this distillation boundary. I can end up somewhere here. So if I do distillation, this is my feed, I end up with here. I'm in the two-phase region. I get a ethanol water benzene layer. I get a water layer with lot of ethanol but lot of benzene also, and I end up with organic region with a lot of benzene, but ethanol also is there and water also is there. So now the organic phase, this is your organic phase and this is your aqueous phase. The aqueous phase can go to the second distillation column, that means this phase, and I can get water at the bottom, and top can be, say if I am doing this, I can end up with this as a ethanol rich phase, this will be a homogeneous mixture. It will not be splitting into two phases, but it will have a lot of ethanol, water as well as benzene, which I can send it to a decanter and I can send it back into the column. I can do condensation and send it back into this column, which has a lot of ethanol, which can go to this ethanol recovery column. The organic phase, which contains essentially a lot of benzene, can go back as to this azeotropic column. Okay, do you realize? That's one possibility. Another possibility is to use a pre-concentration column, 4 columns. Then that pre-concentration columns I could recycle. I could straight away go to the second column. You see, let's go back here. So one possibility is to reach the, using the pre-concentration column. Let me rub out all these arrows. Using the pre-concentration column, we reach very close to this azeotropic composition. Now I add benzene, so I would be somewhere along this line joining benzene and this azeotropic composition. Maybe I end up somewhere here. And then second column, if I go to, I will get pure ethanol at the bottom, and top would be this two-phase mixture somewhere here, right? So this is another possibility. Second column, I get ethanol out. I reach the second part, the upper part of the distillation boundary straight away, and then I could have my benzene phase, organic phase benzene, which can be recycled back, aqueous phase containing a lot of ethanol and water and benzene, which goes to the second distillation column and third distillation column. So these are like two distillation columns in series. It is like your feed of this, you are going to put it into the column. Bottom of this third column is you are putting into the second column. It's just a matter of convenience that we split into two columns. We get water out at the bottom, and we get a benzene rich stream which we can recycle back to the, either from the third column benzene rich stream, or from the fourth column the ethanol water azeotrope, which we recycle to the second column. So think about this, think about these two strategies. Okay, or in a two-column strategy. So think about this pre-concentration column could be here. This would be a pre-concentration column. I get out water. I add the benzene and I do the distillation. This is our azeotropic column. I get ethanol at the bottom, and then whatever comes at the top, I just separate into two phases: aqueous phase, which I recycle back to the first column, and the organic phase, which contains a lot of benzene, I recycle back to the second column. Right? So two column, three column, four column, just a matter of convenience, just a matter of which side of the distillation boundary we are ending up into. Okay, so read more about this ethanol water separation using benzene. Benzene is just one of the possible entrainers. There are many possible entrainers as well. So I would like you to think about what we have done so far. We have looked at three ways of separation. One of the ways was to look at extractive distillation using heavy entrainer. Preferentially, one of the component, the entrainer that we have added, preferentially likes or preferentially has affinity towards this one of the components. Or azeotropic distillation, the light entrainer forms an azeotrope, either homogeneous or heterogeneous, forms an azeotrope with one of the components. So what is our strategy for separation? What is our strategy for separation? Can we think about what is our strategy for separation? What do you think is our strategy for separation? Can we now make some generalizations? Can we make some generalizations? Let's do this properly. Let's make some generalizations. Right. I want you to think about all these three types: homogeneous extractive distillation using heavy entrainer, azeotropic distillation with a light entrainer, homogeneous or heterogeneous. They form two phases. Okay. Can we think about some strategies, some generalizations for us to do distillation? What are the general things that we can use? Or what is a, rather than saying general things, what is a strategy that I could employ? One strategy that we are employing, let's say A and B form a mixture, they form an azeotropic mixture. I add component C. This component C, if it is light, it will go to the top of the distillation column. It may also form azeotrope with either A or B, and it would either form a homogeneous azeotrope or an heterogeneous azeotrope. So you could have a heterogeneous azeotropic distillation. So light entrainer means we call it as an azeotropic distillation. Or C can be heavy, means it will go to the bottom of the distillation column, then we call it as an extractive distillation. That's what we have seen. Now extractive distillation, if I have to think about, I have to have C which has preferential affinity to either A or B. So if I have A and B mixture, I add C to that in a distillation column. This C is going to come down. Along with this C, either A would be there and then I will get B distilled out at the top, or B would be there at the bottom and then A would get distilled out at the top. That means C has to have preferential affinity either for A or for B. Now turns out that we don't have to have C which is a solvent all the time, which is a liquid all the time. So people have looked at different kinds of extractive distillations, which is a non-volatile C. So this C could be an ionic liquid. It does not vaporize at all. But that ionic liquid will have either preferential ability for A or B. That will go to the bottom of the distillation column. Or C can be salts. Salt, if one of the components of A and B is water, then that salt would like water. Right? So look at do a literature survey, even if you just do Google search extractive distillation using ionic liquid or extractive distillation using salts. One of the examples of salts is, suppose I have a nitric acid water mixture. Nitric acid and water form an azeotrope. Either I could have a salt or I could have H2SO4 as a component C, which has a good affinity for water. It will extract as if water will be held in the liquid phase more. HNO3 will be thrown out more into the vapor phase, as if the salt or H2SO4 that we are adding is reducing the activity of water, and it is helping water to remain negative deviation from ideality, gamma less than 1. Okay. HNO3 goes to the, more of HNO3 goes to the vapor, as if I have increased the relative volatility between HNO3 and water. So even if A and B do not form an azeotrope, but they are having very close boiling points, I could use this strategy. So acetic acid water, perhaps I can add salt and make water stay back more. Right? Doesn't happen much with acetic acid water because they are all very small compounds. Acetic acid is a small compound, but nitric acid water, definitely it can be done. It is done in using salts. New areas of research are using ionic liquids to do extractive distillation. Light azeotrope. If water is there as one of the components A or B, I can always add a component. Suppose A is water or B is water. If water is there as one of the components, we could always add an component C, which is like benzene, toluene or xylene. We have seen benzene being added for ethanol water. We have seen toluene being added for pyridine water. But we could also add xylene or other compounds, other organic compounds which form an azeotrope with water, and it forms a heterogeneous azeotrope. So wherever water is there, we could think about heterogeneous azeotropic distillation. Or butyl acetate. We saw so many compounds. Butyl acetate. When acetic acid water was to be separated, we added butyl acetate, because butyl acetate water formed two phases and it forms an azeotrope which goes to the top of the column. So azeotropic distillation using butyl acetates or using xylene. We could do acetic acid water separation using xylene. We could do acetic acid water separation using benzene, right? So think about all the strategy that we have adopted. Can we think of a generalization? And if I can think of some general concepts, then we could think about using it for any other type of distillation. So this is what I was just talking to you about. We talked about azeotropic distillation. We talked about extractive distillation, right? Remember, extractive distillation, we could think about using any other non-liquid components as well, using ionic liquids or salts or nitric acid water, for example. Right? Just do a Google search, extractive distillation using ionic liquids, extractive distillation using salts. If water is one of the phases, then we could use benzene, toluene, xylene, butyl acetate. So many things we could use which form an azeotrope with water. Water forms azeotrope with many compounds. And it would become a heterogeneous azeotropic distillation. Right? Above all, in spite of whatever is there, we need to draw residue curve maps, and we need to think about distillation boundaries so that we could decide what could be the column sequence, what could get distilled out, right? So think about all these things that I have talked about in last 5 minutes or so in context of this classification. What component C I could add, right? If I tell you an unknown mixture of A and B, you do not know, nobody has separated that ever in the world. What strategy do I want to use? Do I want to use extractive distillation? I want to have a component C which has a preferential affinity. Say for example, just give me one more example, then we will stop. So suppose one of the components is like an amine, right? say RNH2. I could use a component C which could be like HCl. Then this RNH2 will form a salt, RNH3 plus Cl minus. It prevents this B from having any vapor pressure at all. It forms a irreversible salt, if you like. We could use this carbon dioxide as a component C. Separations using carbon dioxide, especially for amines and things like that. Right? So think about what you want to separate, A and B. What is the property of A and B that you can take advantage of to increase volatility of one over the other? Either that volatility is by forming an azeotrope with compound C, like benzene, toluene, xylene, butyl acetate, or using an extractive component C, which will preferentially hold back one of the components in the liquid phase, reduce its activity, negative deviation from ideality, gamma less than 1, make it preferentially remain in the liquid, it thereby increase the volatility between A and B. Right?